Looking at a map of the world, it appears that the eastern edge of South America and the western edge of Africa could fit together like interlocking puzzle pieces. Scientists have long noticed the similarity between the two coastlines, but it was not until the 20th century that evidence could support a theory that the continents were once connected. In 1912, a German meteorologist named Alfred Wegener introduced the first detailed and comprehensive theory of continental drift. He argued that the continents had once formed a singular supercontinent that he called Pangaea, which means all lands. Over millions of years, Pangaea broke into several fragments, which began moving away from each other, slowly drifting to their current positions on Earth's surface. Wegener supported his theory by demonstrating the biological and geological similarities between continents. South America and Africa contain fossils of animals found only on those two continents, with corresponding geographic ranges. One of these animals, an ancient freshwater reptile named Mesosaurus, could not have crossed the Atlantic Ocean. Instead, Wegener proposed that the animal lived within the rivers and lakes of a singular landmass which later broke apart. Other fossil evidence also supports the theory of continental drift. The earliest marine fossils found along the eastern coast of South America and the western coast of Africa date from about 150 to 200 million years ago, suggesting that the Atlantic Ocean did not exist prior to that time. Ancient rocks on the Brazilian coast also match those found in West Africa. But how would such large landmasses move? The theory of plate tectonics argues that Earth's outer layer, the crust, is composed of large plate-like sections of solid rock. These crustal plates essentially float on weaker layers of partially melted rock in the mantle below. Scientists believe that convection circulation within the mantle helps continents to move. As heat from Earth's innermost layer, the core, transfers to the bottom layer of mantle rock, the rock warms, softens, and rises upward. This pushes cooler rock downward. The cycle repeats, creating convection currents. This churning motion in the mantle appears to be a major factor in plate movement. The plates, and thus the continents, are still moving today, at an average rate of less than 5 inches per year.